All righty, gang. Hello, hello, and welcome back here. So today we're going to look at some more ideas of discontinuity, but we're going to look at it in terms of a specific type. And this one is what happens when a graph at a particular x value approaches infinity. All righty. So let me go ahead and draw a little bit here. So I'm going to essentially put a dashed line saying, hey, we're getting really close here to this value, but we're not getting there. And just for the sake of argument, let's just go ahead and call this value right here, we'll call it C. So we'll make that C. So this is C. So say I have a graph that's approaching this value of C, but it takes off. Maybe the other side goes the opposite direction. Or not even that, maybe the graph goes in the same direction. Here's what I want you guys to try to figure out. For these functions f of x, so we'll call this one f of x. We'll call this one g of x. What I'm wanting to know is, as x approaches c from the negative side, what does our graph equal? What does our function equal? As x approaches c from the positive side, what does the graph equal? And how about just in general, the graph itself? And likewise, we'll do the same thing over here as well. So I want to know the limit of g of x for the value of c from the left side, the right side, and the overall limit. So once you guys go ahead and start working on this a little bit, and I will keep doing this. All right, so for this one right here, as it goes from the left side, the graph is approaching, from the left side, the graph is approaching infinity. So we'd say that it equals positive infinity. We're going to come back to this here in a second because there's something we got to add to this. If it's approaching from the positive side, it's going to negative infinity. But what about this one? If one's going to positive infinity and one's going to, that actually looks like 8. One's going to negative infinity. What would this be? Well, since they're not equal, we learned last time that that would be does not exist. Because, again, the two limits do not agree. So just like we said last time, it doesn't do us any good to just say does not exist. We always got to make sure that we are giving our reason for why we believe what we believe. Always got to be able to support it. You don't want to ever just have uh, be able to just kind of hold truth to things without actually having a good idea why you hold the beliefs you do, why you think the way you think. You need to always be able to think that through, not just math, but life in general. You need to be able to support why it is you believe what you believe, not just because people tell you. Why does that hold true? Well, now let's look at these positive, negative infinities. This idea that it approaches positive infinity, that is not doesn't seem compatible with an idea of a limit. The idea of a limit is that it's kind of holds into some specific value that it goes to. But if it's infinity, then it's going off into something that is boundless. A limit says where is that value that the graph is bounded to, goes to, where infinity says it's going to go off in no man's land and it will be unbounded. So although the limit does equal positive infinity, we still would come back and say, though, that this limit does not exist. Even though this limit goes to negative infinity on this one side, we'd still say that it does not exist for the sheer fact that even though it is bounded, or even though it does go to that positive infinity, it does go to that negative infinity, those are without bound. And when they go without bound, then it ultimately does not exist. So technically, we would say the limit as x approaches c from the negative side is positive infinity, but then we'd follow that up with the limit doesn't exist. Both things are true. So let's take a look at this one. Notice here from the left side, it goes to positive infinity. Here from the right side, the positive side, also goes to positive infinity. And since they both equal the same thing, that means this also is equal to positive infinity because they are equal. And again, I should probably write that. Because the limit because they actually agree. However, that being said, we are talking about going to infinity. Unless you're Buzz Lightyear and you've gone even beyond infinity, none of the rest of us have ever reached there. So we still would come back and still say, though, that the limit does not exist. Anytime a graph goes to infinity, we'd say that it does not exist. So now let's think about what those red lines are up there. Those red lines are, well, before we've called them asymptotes. And we said an asymptote is a vertical line that the graph never reaches. I think we can probably come back with a better definition, a better reason for what a vertical asymptote actually is. Let's see if you can't take a second. Go ahead and pause. See if you can't take a second and try to write out what a definition might be for an asymptote in terms of a limit. Okay, well, let's see if we can't take a little shot at this here then. So I'm using my magic eraser here. Hopefully that gave you guys enough time. Here's what we essentially come back and say. We say that a vertical asymptote is not a line that we get really close to and never reach. A vertical asymptote, this is a value of x for some f of x, some function, we'll call it f of x, such that the limit of f of x, we better probably call that c. There we go. We'll make this a little cleaner here. Seriously, so much more fun to add sound effects. Or limit of f of x and whatever I'm going to say here. All right, so the limit it's a vertical asymptote is an x value where the graph goes to positive infinity at that value of c, or it goes to negative infinity. And even though I'm putting c here, this could be c from the left side, it could be c from the right side. So it could be a one-side limit as well. It doesn't have to be just the actual value. So turns out a vertical asymptote isn't a line, well, it's a value. It's an x value that when we take the limit of a graph or the limit of a function, it goes to positive or negative infinity. That's what it is. So let's see if we can't actually put this in some ideas. We're going to determine the vertical asymptotes. All right, so we'll first determine the asymptotes from using an algebra perspective, algebra 2 pre-calculus perspective. And then we're going to try to see if we can't figure out what that actually is. I wanted a 3 there. There we are. I like that better. All right. And we'll see if we can't figure out why this actually works. All right. So if we were doing algebra, we would still take this denominator and we would have factored it. So we would have taken the denominator. And we said, all right, vertical asymptote, that's whenever x equals 0 in the denominator, that's the line. But now we know it's not a line, it's an x value. And you would have came back and said, all right, since I have x minus 2 and x minus 3 in the denominator, that means x equals 2. That would be a vertical asymptote and x equals 3. And you're not wrong. And that's still a valid way to figure out vertical asymptotes. But if we're looking at it in terms of a limit, here's what we're looking at. What if I were to take 2? And it doesn't matter. You can call it the negative side. You can call it the positive side. It doesn't matter. And I were to evaluate the function at that limit. So when I put that 2 from the negative side in here, we would have factored that. And I take that 2 from the negative side. Let's think about what 2 from the negative side means. Let's just give ourselves a number line here real quickly. All All right, there's 0, there's 1, there's 2, there's 3. So if I'm talking about 2 from the negative side, that means I'm talking about some number as I'm coming up to 2, getting really, really, really close. Notice it's a number that is a little bit less than 2. It would be like 1.99999. It's some number that's really, really, really close to 2, but not quite there. So if I take this 1.9999999 and I plug it into this, I would end up with a negative, really, really small number. And then 2 minus 3 is still a negative here. So if I were to plug my 2 in here, I would end up with some value. If I plug 2 in here, I'd have 7 on top. I'd have a super small negative small number here. And I'd have a 2 minus 3, that'd be negative 1. Negative times a negative is a positive. So I'd have 7. And this would be like a negative, almost like a negative 0. So I'd end up getting really close to a positive infinity. Any number divided by 0 is some sort of infinity. So this right here, this, I should probably make that like a negative. I should put S in for small, small number. It's really close to 0. 0 times negative 1 is 0. That's where I get my 7 divided by 0 from. But a negative and a negative makes it a positive. So it's positive number really close to 0. Positive divided by positive, that's where I get my positive infinity. So I would then say then I have a vertical asymptote at x equals 2 because the limit of f of x equals if I came from the negative side here, so that'd be a negative side, it equaled positive infinity. Well, friends, why don't you do me a huge favor, and why don't you guys try to deal with this one from, let's do 3. Let's try 3 from the negative side as well. And again, it could be positive, it could be negative, doesn't matter. Let's try 3 from the negative side. What would that look like? Why don't you pause the video here and try it yourselves. All right, here we go. So 3 from the negative side. If I wanted to use a limit definition for vertical asymptotes, and again, our algebra definitions still work, but when we're in calculus, we want to really kind of try to speak calculus a little bit. So now that we know what a vertical asymptote really is, let's look at the limits of that value. So if I take my 3 and I plug it in, I'd be equal to 3 times 2 is 6 plus 3, so I'd have 9 on top. I'd have a positive 1 here, and then 3 from the negative side. So in this case, if I'm coming from the negative side, that would be like coming from right about here. So that would be 2.9999999. You get the idea. So 2.9999 minus 3, well, that'd be a negative, really super small number. And again, this is not the, you wouldn't actually put this part in. You'd leave this out. You just go right from 2x plus 3 over x minus 2x minus 3 equals positive or negative infinity. You'd leave this out. I'm just putting it in there so we can see whether it's a positive infinity or a negative infinity. So positive times a negative is a negative. Positive divided by negative is a negative. This would be a negative infinity. So we have a vertical asymptote at x equals 3 because the limit of f of x equals, in this case, it would have been negative infinity. And again, if it equals, remember, if a limit equals infinity, the limit really doesn't exist because it is unbounded. So we can technically make one more statement. Therefore, the limit as x approaches 3 at f of x does not exist. Yep. So that's a vertical asymptote. All right. We have a little idea, hopefully, now what a vertical asymptote is. Well, let's try this one more time. What if I were to give you a problem like this? And I would like you to try to use a limit definition to determine what the vertical asymptotes are for this function. Feel free to go ahead and use algebra to begin with, but I want you to prove it for me using calculus. So start off with algebra so you can at least figure out what those values are, but then let's use algebra to figure it out. Okay, and go for it. All right, so you look at the denominator here, you see that we have x equals 1. It's not going to work. X equals -1 is not going to work. So you'd tell me that the vertical asymptotes are, let's find out. If I take my 1 and I plug it in here, let's say that x approaches 1. And we'll go from the positive side, I guess. So we have our x cubed plus 1. By the way, I'm hoping you guys all realize something. Hopefully we remembered our difference, or our sums of cubes, and we factored that. And we'll talk about that here in a second to see what that looks like. So we plug our 1 in here, and we have x cubed plus 1 x squared minus 1. So when I factor that top, I factor that bottom, so I'm coming from 1 from the positive side. So I have 2 times 1 all over 2 times. All right, let's see here. 1 from the positive side. If I'm coming from the positive side, that means I'm coming from this direction over here. So that'd be like 1.0000001. It's going to be slightly up the positive side of 0. So that means this would be a positive small number there. So as I've got like a positive 0 almost, I'm going to put a positive small number there. Really, that's 0. That means I have a positive times a positive is a positive. Positive divided by positive, that makes this a positive infinity. So x equals 1, I'm sure you guys came up with, is a vertical asymptote because it approaches positive infinity. Equals 1 because the limit of g of x equals positive infinity. So vertical asymptotes are when the graph or the limit approaches positive infinity. And just for the fun of it, what would have happened if we would have plugged in our -1 there? So we plug in our -1 here. we would have found out that it is 0 over 0. So that tells me it is indeterminate. So go back to our little blast from the past here. We would have done a little bit of factoring here. So our limit is going to exist even though the function value is undefined. That would be a removable point of discontinuity. That means I have a hole. I have a removable point of discontinuity at x equals -1. So we'll finish solving that. Then I'm going to give you guys a couple more limits to evaluate, and we'll call it a day. All right, so we got to clean this up here still. So x squared minus x plus 1 all over x minus 1. I can't believe I just put infinity there. That's going to be tomorrow's lesson. All righty. We have 1 plus 1 plus 1 all over 1 plus 1, or -1 minus 1, sorry about that. And we end up with a -3/2. So it turns out that limit actually does exist. Which is why it is not a vertical asymptote. All right. So hopefully we have a fairly decent idea now what vertical asymptotes are. Let's try a couple more of these here. I'm just going to give you guys a couple limits, and I'd love for you guys to evaluate them. So 3 negative. Oh, let's make this x plus 5 and x minus 3. Love to know what that is. And I also would like to know what this is right here. Let's try x plus. Let's use the same one there. All right, friends, go ahead and take a second, pause the video, and evaluate those if you don't mind. All right, here we go. I plug it in. I get 3. I'm coming from the negative side. So even though this is 0, it's going to be more on the negative side of 0. So I have 8 divided by a negative side of 0. So that means this is going to be negative infinity. And if it's negative infinity, well, we'll come back. We're not quite done with that. This one over here, I'm going to have 8. I'm coming from the positive side. Therefore, I'm going to have a positive side of that number. So it's going to be essentially a positive 0. So 8 divided by a positive side of 0 would be a positive infinity. But as you guys are the most amazing math students you are, I know that you know we're not going to leave the answer like that, because we are going to say, even though it goes to infinity, we know it goes to infinity. We will always show that it goes to negative or positive infinity. So we would come back and say that the limit does not exist. And we do the same thing over here as well. The limit, even though it goes to positive infinity, and you'll need to know that because on some of the free response questions, they're going to have these limits go, the answer for the limit go to positive and negative infinity. And that's okay. It does go to positive and negative infinity, but I want you guys to remember that even if it goes to a positive and negative infinity, even if that's what it evaluates to, that's still an unbounded graph. And that means that the limit does not exist. All right, guys, that was infinite limits. We got one more section here in the first unit, and we will be done with the idea of limits until we come back and look at something called L'Hopital's rule much later on. All right, take care.